Okay, Theorem 16, which is the fundamental theorem of line integrals. If f is a function mapping a subset of n space to the real numbers, so just something like f of x, y, z, for example, if this is differentiable on the domain U, and the curve C starting at the point A and ending at the point B is continuous on U, then the integral over C, so in other words, the line integral of grad f dot dr is f of b minus f of a. So in other words, this can be really easy to calculate via f of b minus f of a. So let's have a look at an example. Consider the vector field f equal to x plus z, comma z, comma x plus y defined on 3 space. Determine whether it's conservative and a bunch of other things. All right, so here we have the vector field. These are the blue arrows here, right? So let's have a little look around it. Looks like a stormy current of some kind, okay? And so we have a point A. Now the point A is in the middle, that's the origin. And then the point B, when t is equal to 1, we have, well, subbing in x, y, z equals 1, well, it takes us to this point, right? So on the vector from the origin to the point. So we're finishing at t equals 1, all right? So when t equals 1, that is our point of termination there. Okay, so we've got our diagram. The curve C is this black curve. Now, is f conservative? So we've got a theorem for this. Remember, it's theorem 8 of chapter 4. So by theorem 8 of chapter 4, if f has continuous partials, partial derivatives that is, and the curl of f is the 0 vector, in other words 0, 0, 0, well then f is conservative. Okay, so let's test this. We've got to calculate curl. Now I like to use my little formula. So curl of f equals ry minus qz, comma pz minus rx, qx minus py. Where in this case, p is the first component of this vector, so x plus z, and q is z, the second component, and r is the third one, x plus y. Okay, so let's calculate this then. R subscript y is 1. Q subscript z is 1. So 1 minus 1. P subscript z is 1. And R subscript x is 1. Q subscript x is 0. And P subscript y is 0. So this is the vector 0, 0, 0. The 0 vector. Okay, so we can conclude that yes, f is conservative. Okay, and since we know it is conservative, we know two things: that the work done is path independent, and that there should exist a potential function, lowercase f, a scalar function, such that uppercase f, the vector field, is the gradient of the scalar function lowercase f. In other words, f equals grad lowercase f. So we can do part 3, find a potential function. Okay, question 2 of this says, if so, calculate the integral of f dot dr over the path c, where c is t squared, t cubed. Okay, so let's do that on this page, and then we're going to need a blank page. So integral over c of f dot dr is equal to integral from 0 to 1. Now this is f of r of t, but r of t is given by this. So we're taking the x value, subbing it in there, the z value, subbing it in there, and so on. All right, so what we have, and this is a dot product, so we have t plus t cubed for x plus z. Then we have z is t cubed, and then we have x is t plus y, that's t squared, and then we've got to dot this with dr on dt. So dr on dt is the derivative of this with respect to t, so it's just 1, 2t, 3t squared. So dotting that with dr on dt, we'll write 1, 2t, and 3t squared. Okay, we've got to take the dot product of these two vectors and then integrate the result. So 1 times t plus t cubed plus 2t times t cubed is 2t to the 4th. 3t squared times t plus t squared is 3t to the 3rd plus 3t to the 4th. Okay, so next we can collect some like terms here. So we have a t, and then we have 4t cubed. Okay, then we have 5t to the 5th, or sorry, t to the 4th. And we need to integrate this. So we have a half t squared plus t to the 4th plus t to the 5th from 0 to 1. Now that gives us 1/2 plus 1 plus 1 minus 0, and so that's 5 over 2. Okay, so the work done in moving a particle from A to B is 5 over 2 units, right? So presumably that's an energy unit, like joules, if it's all in SI units. Okay, so now let's calculate this in a different way, but first we've got to find a potential function lowercase f. So next, and I've got some blank paper here. I hope you have a piece of blank paper maybe on the back of one of yours, but if you bought this printed out for you from the print shop, then you might not have that, and so you'll have to get a blank piece of paper and shove it in there and then maybe staple it or tape it. So sorry about that. I didn't realize that you would need more paper. Okay, so next we seek f of x, y, and z such that the vector field f is grad f. Okay, and so this is f subscript x, f subscript y, f subscript z. And so matching components, we have a system. F subscript x is x plus z, f subscript y is z, f subscript z is x plus y. Okay, so given this system, we want to solve this for the scalar function lowercase f. So we'll just take that first one and integrate partially with respect to x. So f of x, y, z is the integral of x plus z dx. So we have a half x squared plus x z plus some function g of the other letters y and z, right? Because if you look at this and differentiate this partially with respect to x, well, then you'll get x plus z, right? Because this one will differentiate to give 0. Remember, it's a partial derivative. So we would get back this. Okay, so this is f. Now, there's some unknown part of it, right? Which is the analog of plus c when we integrate. Okay, so we need to know that unknown part of it. So to do that, to find what g is, we differentiate and compare with these. So differentiating with respect to y partially, we have f subscript y. Now this goes to 0, this goes to 0, and then we just have g subscript y of y and z. And then we know from this equation right here that that's just equal to z. Okay, now we can differentiate this f equation right here with respect to z partially as well. Okay, so doing that, let's see. That goes to 0, then we have x. So f subscript z equals x plus g subscript z of y and z. And according to this equation right here, this must be equal to x plus y. Okay, now we've got an x and an x matching. So what this tells us then is that g subscript z of y and z is equal to y. All right, so now what do we want to do? Well, let's take this equation and integrate this. All right, so integrating the equation gy of y z equals z with respect to y, and of course it's a partial integral, so we have the integral of z dy is equal to yz plus some function h of the other letter, z. Okay, and this gives us g of y and z. Because we've taken this equation right here and integrated this partially with respect to y, and that should give us g. All right, so this is g. Now, there's a function that we don't know at this point, but we know it's a function of z only. Okay, so now we want to differentiate this expression and compare with this. So correction, the page should look like this. We should have differentiated with respect to z partially so that g subscript z is y plus h dash of z, and then matching that up with this gives that h dash of z is 0, so we end up with yz for g. And so we see then that g of y and z is equal to just y times z, and hence f of x, y, and z is equal to, where was f? Up here. And now we have this, so we have a half x squared plus xz plus yz. Okay, there's our potential function. All right, now for the last part, and we don't have much space for it, but I think it will fit. So for the last part, using the fundamental theorem, f dot dr equals integral over c of grad f dot dr, but now we have the fundamental theorem that we can use. So it's f of 1, 1, 1 minus f of 0, 0, 0. And so just looking at this, subbing 1, 1, 1 in there, we have a half plus 1 minus 0. So again, we get 5 over 2. All right, great. Next, evaluate the line integral. So remember, this is a surface area of a sheet under the surface along the path C. So put F equal to the vector field 3x squared y squared comma 2x cubed y. Okay, and the reason why we do that, and this is PQ, so the reason why we do that, well, if you take the dot product of this with dr, this is exactly what you get, right? So dr being dx comma dy. So given that we have that, we want to test whether f is conservative. Okay, so taking p subscript y, differentiating this one with respect to y, we have 6x squared y. Now that's equal to the derivative of this partially with respect to x. So f is conservative. All right, and so now what we do is we seek a potential function such that f is equal to grad f. Okay, so let's do that. Then that says f subscript x is 3x squared y squared, and f subscript y is 2x cubed y. So integrating this one with respect to x partially, we've got x to the power of 3y squared plus some function of the other letter, say g of y, and that's f. Okay, now differentiating this with respect to y partially, we have 2x cubed y plus g dash of y. All right, now matching these two things, we see g dash of y must be 0. And so we can put g of y equals a constant, but we can even simplify that because we're just seeking 1. So let's choose that constant equal to 0. Okay, so then that tells us that f of x and y is just x cubed y squared. This is our potential function. Okay, now given we've got that, it makes the rest of this really easy because we've got the fundamental theorem that we can use. So it's f of, now we finish here, so f of 1, 0 minus f of 0, 0. Okay, f of 1, 0 is 0, f of 0, 0 is 0, so 0 minus 0 is 0. Now, we can do this another way. We can do this via parameterizing this path right here. You see, since that's path independent, it didn't matter that we took this path or we didn't. We just had to calculate this. Right now, using the path, so let's say via parameterization, it's a bit more work, but we can do it. So we've got r of t. So the parameterization of this, is t comma t cubed minus 3t squared plus 2t, where t is less than or equal to 1 but greater than or equal to 0. Okay, so there's our curve C. And so now what we do is calculate f dot dr. Now we've already done it, right? I'm just showing you how it can be done via parameterization, which is a bit more work. So from t equals 0 to 1, now that's f of r of t dot dr on dt dt. So integral from 0 to 1. Now we take f, which is this, we sub in our parameterization, the x and the y values, into this. So you can see it's going to be a little bit messy. So we've got, what is it, 3x squared, so that's 3t squared. Now y squared is the square of this, t cubed minus 3t squared plus 2t. Okay, comma 2x cubed. Now this cubed is t cubed, and then times y. The y is this, so t cubed minus 3t squared plus 2t. Okay, and then we dot that with dr on dt. Now differentiating this, we have 1 comma 3t squared minus 6t plus 2, and then that is dt. Okay, so we've got to take a dot product of these, which will be a little bit messy, so let's not do that. Dot dot dot, we're supposed to get 0. Okay, now let's see if I can do that here. Just missing the 2 there. Okay, so you can see that that integral as given by Mathematica also gives 0. All right, so moving on. Without using Green's theorem, calculate the work done by the force field F equal to y minus xy comma x squared, and moving an object counterclockwise around a rectangle with the vertices given by these 4 points. Compare the result with example 4.11. Now, just to remind you, so you don't even have to flip back, I'm going to do this via Green's first. So via Green's theorem, the work done in moving a particle around here is the integral over c f dot dr. Now c in this case is the entire path around this rectangle, right? So to do it this way, you have to break it up. But Green's theorem tells us that we can do this via calculating an integral over this region D. And so we've done this already, but I'll just remind you, it's double integral over D of qx minus py dx dy. And so that was integral from 0 to 1 for the y's going between 0 and 1, 0 to 2 for the x's going between 0 and 2. Q subscript x is 2x. P subscript y is 1 minus x. Okay, so simplifying that, we've got 2x minus x is 3x, and then minus 1. So integrating now, we have 3 over 2 x squared minus x from 0 to 2. And so that gives us 6 minus 2 is 4. So 4y from 0 to 1, which is just 4. Okay, so that was pretty easy, right? Now this way requires us to break up each of these segments, parameterize them, and do them one by one, and then add up the result. So C consists of the following 4 segments of that curve. So C1, and we have C2, then C3, and then C4. And they're all linear paths, which makes this somewhat easier. Okay, so the first one from 0, 0 to 2, 0, so from here to here, well, the y value is staying at 0, the t value is changing, right? So that's as t goes from 0 to 2, so here is our parameterization. Now, the next segment has the x value equal to 2, but the y value is changing. And to make this pick up from where we left off on the t's, because it's conceptually easier, we start with t equals 2. Now, if you sub in t equals 2, so we put in a 2, we get 0 matching that. We put in a 3, we get 1 matching that. Okay, and so on and so on. All right, so we want to calculate the integral of f dot dr over c for each of these values of c, and then add the result. So let's just remind ourselves at the top of this page what f was. So here we've got f of x and y equal to y minus xy, x squared. And then c1 is r of t equals t comma 0. T goes from 0 to 2. Okay, so now calculating this, we have the integral from 0 to 2, 0, 2, of f of t and 0. From here, we're just subbing in r of t and taking that dot dr on dt dt. Okay. All right, so continuing, this is the integral from 0 to 2. Now subbing the t, x for t in here and 0 for y, well, we've got 0, and then we have t squared. The derivative of this is 1, 0. Okay, so 0 to 2. Now the dot product here is just 0, so 0 plus 0 is 0. So this integral is 0. All right, so back to the picture, you probably see, so there's no work done whatsoever along that segment down the bottom, right? Because all of these field arrows are perpendicular, so they're not pushing you left or right, right? So there's 0 work in getting from there to there. Okay, now doing the next one, let's remind ourselves what C2 was. We had 2 comma t minus 2 for t between 2 and 3. Okay, so f dot dr. So we've got an integral from 2 to 3. F of 2 t minus 2 dot dr on dt. So dr on dt here is the derivative of this. So in other words, it should be 0, 1. Okay, so taking that dot product. So 2 times, oh, hang on, we've got to sub this in first, right? So subbing that into f, and there's f, we have, this is our y, so t minus 2 minus 2 times t minus 2, and then 2 squared, dotting that with 0, 1, and then take dt. All right, we don't even need to simplify this because you can see that this gives 0 and then plus 4. So we've got the integral from 2 to 3 of 4 dt, and so this gives us, it gives us, let's see, 12 minus 8, which is 4. Okay, moving on to the next one. So that's 4 units of energy in the next line segment. All right, so the third one. So in the third one, we have, let's see, C3 is R of t is 5 minus t, comma 1. So R dash of t is minus 1, comma 0. So this is the integral from 3 to 5 of f of 5 minus t, comma 1 dot dr on dt. Now dr on dt is there, but we've got to sub this into f. So we get, so y is 1, and so we have 1 minus brackets 5 minus t. Okay, and then we have x gets squared, so that's 5 minus t squared. And then we're taking the dot product with minus 1, comma 0. Okay, so now taking the dot product gives us just the simplification of this, because then it gets multiplied by minus 1, and then we've got 0 times this, and we add those together. So that's plus a 0. So we need to just simplify this and multiply it by minus 1. So we have minus 4 plus t, so t minus 4, and then times minus 1. So minus t plus 4, and then that's dt. Okay, integrating that gives us minus a half t squared plus 4t, right, from 3 to 5. And so we get 20 minus 25 on 2, minus 12 plus 9 on 2. And so that adds up to 0. Okay, now let's take this last little piece. So along C4, we have the integral from 5 to 6 of f of, now that was, C4 was the path, r is equal to 0, comma 6 minus t. So f of 0, 6 minus t, dot the derivative of that, dr on dt, is 0 minus 1. Okay, so simplifying this, we've got to sub this into our f. So that's x is 0, so we just have 6 minus t, comma 0, dot 0 minus 1. Now this dot product is 0, and so we get 0. Okay, so we've worked out the work done on each of the 4 segments, and so now we need to add those together. So adding those together on the next page, we had 0 for that one, we had 4 for that one, 0, and then 0, and so we got 4. All right, so that agrees with what we got in Green's theorem. So I'll just remind you, in Green's theorem we got 4, and this is what we had to do. So this was way easier, right? But nevertheless, it's useful for you to be able to see how this works via parameterization.